carbon dioxide at 225 kPa and 330 degrees C flows in a pipe with a volumetric flow rate of 8,500 liters per second. Determine the specific volume in meter cubed per kilogram and the mass flow rate in kilograms per second. So we have some sort of pipe, and we're given information that it's the CO2 at a given pressure, 225 kPa, and temperature of 330 degrees C, and it has a volumetric flow rate. AV is a symbol used in the textbook, and I like to use it as well for volumetric flow rate. Some other textbooks will use Q, but we've already used Q for heat transfer, so just use AV. It's the A, which is a cross-sectional area, times V, the velocity, gives you the volumetric flow rate. So that volumetric flow rate is 8,500 liters per second. And right away we can convert that to 8.5 meter cubed per second. Why? Because there's 1,000 liters is 1 cubic meter. All right. Likewise, we can convert this temperature up here. I suspect we're going to need to treat the CO2 as a gas, as an ideal gas, or see if it is an ideal gas, real gas at least. And so we can convert this to 603.15 Kelvin for the temperature. Okay, so how do we calculate that specific volume? Well, if we use the ideal gas equation, we have that PV is equal to RT divided, well, I'm going to do this, put that P on the other side, RT over P. And so we have to get the gas constant for CO2. That's the universal gas constant divided by the molar mass of CO2. So 8.314 kPa meter cubed per kilomole Kelvin. That's for R bar, the universal gas constant. And then we have for the molar mass of CO2, we look it up in our textbook table A1, it comes back at 44.01 kilograms per kilomole. And so the per kilomoles, they cancel, and we're left with kilopascal meter cubed per kilogram Kelvin for the gas constant for CO2. So the only other thing that we probably want to check to see if we need a compressibility factor for this problem. It looks like it's going to be an ideal gas, but what we can do is we can get not just the molar mass of CO2, but we can get the critical temperature. So T critical for CO2 out of table A1 well, I shouldn't do it like that, put it like here, is equal to about 304 Kelvin. So that T sub R, the actual temperature divided by critical point temperature, comes in at 1.98. Likewise, the critical point pressure is 73.9 bar. And so P sub R, the actual pressure divided by the critical point pressure for the CO2, comes in at 0.030. So this is an extremely low P sub R. If we go to the table, or not the table, figure A1, we look for that reduced pressure. That reduced pressure is going to push us down in the 0.3 range right in here. Let me take a look. 0.03, sorry, even further, way over here. And then the T sub R was close to 2. There's a line, T sub R close to 2. It's tucked up here. The compressibility factor Z is about 1. You would treat it as an ideal gas. We have justified treating this CO2 at this pressure and temperature as an ideal gas. Okay, so let's go back here and continue the calculation. So V is, the R for the CO2 is 0.1889 kilopascal meter cubed per kilogram Kelvin, multiplied by the temperature, 603.15 Kelvin, divide by the pressure. The pressure is 225 kPa, and we get a specific volume of 0.5064 meter cubed per kilogram. Box it, call it the answer for part A. Okay, the next question is, what is the mass flow rate? Well, the mass flow rate, mdot, is related to the volumetric flow rate, AV. And so if I had density, I would multiply by density. So rho AV would be the mass flow rate, but in Thermo 1 we like to use specific volume, and so the reciprocal of the density is the specific volume. So we just have our volumetric flow rate, 8.5 meter cubed per second, and divide by the answer for part A, 0.5064. If you want more digits, it's 0.9. Then it's meter cubed per kilogram. The meter cubes go, and we are left with mass flow rate coming in at 16.79 kilograms per second.